Hello and welcome to an AP free response question. I'm your host, Mr. McMahon. I hope you are having a wonderful day. I'm sure you were having a wonderful day until you saw this problem, but that's okay. We're going to break it down. Hopefully you gave it a good shot, and I'll have to clarify some things along the way. First thing you probably notice is there is a not-so-secret edit to this problem. That is because some problems ask for trapezoidal sums, and we did not go over those. So I adjusted this as well as the scoring guidelines to only cover things that we knew how to do. So anyway, let's go ahead and read out the problem. So the height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. So they're giving us raw data. And outside of the data, we have no idea what this curve looks like. All we know is that, well, there's some tree that's just growing. And I mean, you can see that if you look at these numbers, of course, they're increasing that way. Right? That's the output of the function. It's getting bigger, right? Because the height of the tree is getting taller. Okay, so that's my situation. Part A, use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. So for AP FRQ questions, if they give you a second follow-up sentence, it's very likely that they're splitting this question up into multiple points, where you get points for answering the first statement or sentence, and then answering the second one. So we got to make sure we have the right units and actually explain what our answer means. You can't just give the number as the answer and be done with it. Right? That will get you at least the first point. It's not going to get you all of them. So anyway, use the data in the table to estimate h prime of 6. Well, h prime, if we had an actual equation, we could actually just take a derivative and then plug in 6. We can't do that. Right? We notice that 6 should be in between those two, right? But it's not there. But to estimate, we could do we could essentially take what we know as the approximation of the derivative and just use that as an estimate. So let me clarify what I mean. And I'll go ahead and make this graph because it will probably be pretty important later on as well. So let's just make a graph of the data just to start with. So I'll put the t on the x-axis, put the h of t up here. It's in meters. That's in years. And let's see, we go from 2 to 10. So we'll go ahead and put 10 over here. Let's see, let's go ahead and put maybe 5 here. Whoops. 5 here, 6, 7, 8, 9, 4, 3, 2, 1. So here's my 2. And we only have data from 2 to 10. Let's see, my data ranges over 1.5 to 15. So I'll go ahead and put 15 up here. And let's make this maybe 10 and this 5. You want to try to be as accurate as you can. Whoops, it's not quite right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15. The AP is not going to give you any points for your graph. You'll see in the scoring guidelines, but this will help us out tremendously. So we have our data points. Let's go ahead and plot those. 2, 1.5. That's going to be this point here. We have 3, 2. It's going to be a little bit higher. We have 5, 6. It's going to be a little bit higher over here. We have 7, 11. It's going to be up here. And then we have 10, 15. All right, that's going to be way up here. Right, and I'll go ahead and let's go ahead and mark these coordinates. I'm just trying to organize my data as much as I can before I start doing calculations. Otherwise, probably going to get pretty lost here, right? Or going to make a very simple mistake that's going to cost me some points. And I ain't about to do that. So I've organized the table in a much better way. I can actually do Riemann sums here. I can find estimates of slopes, which in fact, that's going to help me with A, right? So what I'm essentially going to do is estimate h prime of 6. All right, so 2, 3, 4, 5, and 6 is here. We don't have a data point for that, but we can essentially just say, well, we don't know where this data point is or where the tangent line is or anything. Let's go ahead and use the slope between these two as our approximation, right? So you want to choose essentially a point to the left and a point to the right of whatever input they're having you estimate the derivative at. Right, so we can say part A, h prime of 6 is approximately just the slope between those neighboring points, right? And usually that actually tends to do a pretty good job. So this will be 11 minus 6 over 7 minus 5. In fact, I should go ahead and change those. Oh, whoops. I should change that equal sign to squiggly bracket because we know that the derivative might be something entirely different, right? So 11 minus 6 is 5. 7 minus 5 is 2. It's a weird 2. And so this is 2.5. What are the units here? Well, we have meters and years. This is a slope between those two, right? So this is meters per year. Right, so you would probably get 1 point for just getting that. You're also going to get another point if you interpret it correctly. So what we might say for the interpretation is that the tree, what is that? Tree is growing at a rate of 2.5 meters per year, approximately at 6 years. All right, or some kind of variation of that interpretation. The main point is once 6 years has gone by, or once you get to year 6, then that is approximately the rate at which the tree is growing. And so you'll probably get a point for both of those. We'll see in the scoring guidelines in a bit. B, explain why there must be 1 time t for 2t10, so t between those two, such that h prime of t equals 2. So this one, when I first saw it, kind of stumped me. Didn't really know quite what to do with that. I had a vague suspicion that I'd end up be using maybe the intermediate value theorem or mean value theorem, and I sort of just followed that intuition and played around with the numbers. But it's not going to jump out at you. But what you might try to do is you say, okay, they're basically asking me when, is there a way I can show that this is going to happen at some point? And you do have to prove it, right? You can't just say, well, the graph kind of looks like that. But if I can show that sort of the slopes are maybe going below or above 2, or even if I can find 2 points that the slope between them is exactly 2, I can immediately invoke the mean value theorem, right? And so we can try to calculate maybe some slopes here. Like for instance, this line we drew over here, right? Let's do a quick slope. That's 11 minus 6 over 7 minus 5. That's going to be 5 over 2 for this slope. It's not going to work. What about this one? 15 minus 11 is 4. 10 minus 7 is 3. That's 4/3. Okay, so this slope over here is approximately 2.5. This one is approximately 1.3. So we do know it's going to happen somewhere. Right? Let's see if we can check some other places here. What about this guy right here? 6 minus 2 is 4. 5 minus 3 is 2. Oh my gosh. That's a slope of 2. Right here. That's it. Right. So, if you remember the mean value theorem, right, just to refresh you guys. The mean value theorem said, make a note of it down here, that if I have 2 points, doesn't matter where they are, essentially I can find the slope between those 2 points. All right, so this would be your M. And if I draw any continuous closed curve going from this point to the other point, no matter how I draw it, as long as there's no breaks in it, there is guaranteed by this theorem at least one spot. In this case, we got 2. At least one spot where the slopes are also M. Right? And so in this case, because we found 2 points where the slope between them was 2, and we know that obviously trees grow in a continuous way, that no matter what the curve is that connects those 2 data points, there's got to be some spot there where the derivative equals 2. So we could say for this part, we could say this is the mean value theorem. By the mean value theorem, right, we have that, I guess one way to say this would be that h of 5 minus h of 3 over 5 minus 3 equals 2, which means that there exists some number, we'll call it C, where C is between 3 and 5. So that h prime of C equals 2. So that's how you'd have to explain it. And you do need to get pretty detailed. Rough, like non-detailed answers are probably not going to get you the points there. Okay. And let's move on to part C. I'll do this in blue here. Use a left Riemann sum with 4 sub-intervals indicated by the data in the table to approximate the average height of the tree over the time interval from 2 to 10. All right, so there's a couple things I want to point out here. Number 1 says use 4 sub-intervals indicated by the data. Right, so normally when you guys are working with functions, you usually make all the intervals equal widths, right? And that's because you actually have all the points on the entire function. Here we only have a certain number, right? And they're sort of sporadic. They have different distances between them. So our rectangles are going to vary. Their widths are going to be different, right? That's what they mean by indicated by the data. They also want us to approximate the average height, right? And once we get to the end of the calculation, I'll have y'all think about this a little bit more, but just realize that the Riemann sum that we're going to do here, if you notice what we're doing, we're essentially taking meters times time, right? Or meters times years. And so the answer that comes out of our Riemann sum is not going to be a height, right? It's going to be something else. I don't know what a meters times a year looks like, but I know it ain't going to be the answer they want, right? And so, you might want to think ahead towards how you're supposed to deal with that. But let's just do the Riemann sum because you do get points just for having the answer and the right units. So, our left Riemann sum is probably going to look something like this, right? So we want to extend the rectangle until we get to the next data point. So we have a rectangle there, rectangle here, right? We've got a rectangle here. It's at 10. That's why drawing this graph was so useful, because now we can see pretty accurately what the widths are, what the heights are, right? This is a width of 1. This is a width of 2. This is a width of 2 again. Maybe I'll put the numbers down here. 1, 2, 2. Scratch these out. And then we have a width of 3 at the end. And then the heights, well, they give us the heights in the table, right? So that's going to be the 1.5. This is 2 right here. There's 6, and there's 11. Right, so the more organized you can make this data, the less likely it is you're going to get confused along the way. So how do I normally do a Riemann sum? Let's forget about the average height part first. So a Riemann sum normally is just the area of all these rectangles. Right, so let's do that first. So I'll call this R for Riemann sum. My Riemann sum is going to be, I don't need parentheses here actually. It's going to be 1 times the height of that rectangle, which is 1.5, plus 2 times the height of that rectangle, which is 2, plus 2 times the height of the third rectangle, which is 6, plus 3 times the height of the fourth. All right, so that's 11. They asked for a left Riemann sum. Let me go ahead and calculate what this is. Let's see what R is equal to. And let's see, 1.5 plus 4 plus 12 plus 33. You will have a calculator for this FRQ if you didn't. Well, I guess it doesn't say here, but you are allowed a calculator on this one. I should have mentioned that at the beginning. We get an answer of 50.5. So 50.5 is just the Riemann sum. Now, when they're asking for the average height, think about this, right? The units for this 50.5, right? We're calculating areas here. We're taking base times height, right? Well, my base is years, my height is meters, so the units for this are meters times years. Again, I don't know what that is. I just know that doesn't look right. And obviously, if I am looking for an average height, I got to be left with just meters. So intuitively, you might realize that we have to somehow get rid of these years here. And this is where, if you think about how grading works, right, just in regular school, that you have weighted categories, right? We're kind of doing the same thing here, right? You can think of these widths, these varying widths of the rectangles as we're doing like a weighted sum here. And if I wanted to change this to an average, I would just divide the total by the sum of the weights, right? So let me sort of break that down, right? I would essentially take this weighted sum, which is like this, and I would divide it by the sum of the weights. So that's going to be 1 plus 2 plus 2 plus 3. Right, and that's going to give me a denominator of 8. And you notice, right, the weights, what are my weights, right? This, those are in years. So my total down here is going to be in years. My weighted sum up here is meters times years. And so the years are going to cancel in this calculation. It's just beautiful, right? So this is going to be 50.5 divided by 8, right? Meters times years over years. Again, those years cancel, right? And we're just left with meters and a final answer. So 50.5 divided by 8 equals 6.31 meters. Right. So that is essentially the average height of the tree, based on our left Riemann approximation, our left Riemann sum, right? Which, obviously there's some room for improvement. There's some empty spaces right there and there. So it's an under approximation. Oftentimes in these FRQs, they also ask you whether or not it's an over or an under approximation. And, well, you can't really just say, oh, it's because it's an under approximation because of the way the graph looks. That's not going to get you any points. So think about, if they were to ask you that, how you would actually mathematically explain that. And I'll give you a hint. It involves derivatives of the curve. So anyway, here's my answer to the FRQ. So you might not have all this stuff on your page. It might look completely different. That's okay. So at this point, this is sort of the phase 2 of that email I sent, right? You want to go ahead and swap FRQs with somebody, or hopefully you have someone else's in front of you maybe, and we'll go ahead and go over the scoring guidelines. So let me jump over there. Scoring, FRQ. So we'll start with part A, right? So looks like we made the right approximation here, right? So we used exactly that, and we got 5/2. In fact, they didn't even include the units here, but you should always include units, right? So we have the estimate. It looks like I got that point. You get another point for the interpretation with units. So there's the units, right? So let's see if my interpretation sounds good enough. So they say h prime of 6 is the rate at which the height of the tree is changing in meters per year. Let's see, I think I had those units. At time t equals 6 years, right? So you also need to specify the time. And let me just double check that. Did I have those units? Yeah, so there's my units there, right? So we had this guy right here. We also specified at 6 years. So this is, let me do this in a completely different color so it stands out. So because we had this and because we specified the time, we had the units, we had the right number, that's plus 1 point. And we also got the right number up here. And really, they only cared about this number for the first point. So that's your first point. So it looks like we got 2 on part A. Let's go over scoring guidelines for B. All right, so notice here, they do the same calculation that we did, right? So h of 5 minus h of 3, that gave us 6 minus 2 over 2, which equals 2, right? So they're calculating the slope between those 2 points, just like we did. Right, and here's how they explain it. Because h is differentiable from 3 to 5, h is continuous on 3 to 5. By the mean value theorem, there exists a value c in between these two, we did say that, such that h prime of c equals 2. So let's see what the point breakdown is. So we definitely get this point over here. And then this point over here, I could go 50-50 on whether I actually get this or not. Because one thing I didn't mention that they did was they explicitly mentioned that it's differentiable on here. I didn't mention that at all. But that is a requirement for the mean value theorem. So it does kind of need to be said. And they also mentioned that h is continuous from 3 to 5. These are things, I think I mentioned the continuity verbally, but I didn't actually write it down. So what they might say is, well, we didn't justify that we could actually use that theorem, and so we didn't use it in a valid way. So I guess what I'll say is, I probably got this point. I forgot to check that off up there. But I probably didn't get this point. I used the right theorem, but I didn't actually justify it. You can't just use a theorem just because you want to. It's got to meet certain requirements. So I probably didn't get that point. Depends on how nice the grader is. Some graders are a little bit nicer than others. Right. So I definitely get a point for this guy right here. Right. That's my plus 1 point. Cool beans. All right, and then we have part C. So let's see what the guidelines say about part C. All right, so they use a lot of fancy stuff here. You notice they're using a definite integral. We've barely touched that in our class, but all you really need to know, right, is that this is equal to the true area under h of t, whatever h of t is. Again, we weren't given the function, so we don't know. We have no way of knowing, really. But that's all it stands for. That's all you need to know right now. So they give you 1 point for the sum, and then 1 point for the approximation. Right? And so is that right? Let's see. 1 point for the sum, 1 for the approximation. I guess what they mean to say is, oh, and this part is incorrect based on the way I revised the problem, so we should get rid of that. I believe what they mean to say is that the sum is just the adding up the areas of the rectangles, right? That's just what a Riemann sum is. And the approximation is the approximation of specifically the average height. So one way you could look at it is this part right here gives you 1 point if you do just that part correctly. And then you get the second point for this part here. So did we do that? Well, you see here from my revised scoring guidelines, I didn't quite set it up quite like this, but I think they would probably give me credit for doing that part right there, right? Because if I look back at my blank, we did calculate the sum right here, right? So that's going to give me a +1 for sure. And then our approximation for the average height is over here. So I'm guessing, unless I'm misreading something, I'd probably get that point over there as well. So it looks like out of, see how many points were total here. We had 6 points total, right? And it looks like I got this one, got this one, got this one. I missed that mean value theorem. Even though I did it correctly, you guys might be surprised. Some AP graders are really, really nitpicky. Even if you, quote unquote, do the right steps, if you don't justify correctly, they'll snatch that point away from you. So it just goes to show you, you always got to make sure you know what you're actually doing. It's not enough to simply just memorize a bunch of steps or memorize a formula. You have to know what it means and know how to manipulate it. Right? That's how you get the points on the AP test. So anyway, I hope this was helpful. Again, another announcement about that quiz next week, right? So the best way to prepare for that, in my opinion, is really just making sure if I gave you a really simple function and I said, give me a left Riemann sum with 4 subintervals, that you could actually calculate it by hand. Or a right Riemann sum. Those are really the only two I want to ask at this point, because it's just too much to involve the midpoint, and you guys have not had enough practice with that anyway. Let alone trapezoidal sums. We'll get to that later. Trapezoidal sums are a little bit more accurate, and if you want a sneak peek at what exactly they look like, right, let me do maybe a little mini lesson down here. If you just wanted to know the AP problems, though, I'm done at this point. But for those who are curious and who are bold enough to continue learning. All right, so let's say I have something like this. Yeah, let's extend that out. So a trapezoidal sum would essentially, you would still create the subintervals. Right, so we just draw a line down from each of those, but then you would directly connect these points, right? You would do something like this, and you create these little trapezoids, right? So if you were given raw data, right, this is sort of the way it might look, but also you could do trapezoidal sums for any generalized function, right? So if I had some sort of squiggly-like function like this, and they say, what is a trapezoidal sum in, let's say using 4 equal subintervals from 2 to 6. Well, I just have a trapezoid for each unit, right? So that's 3, 4, 5, here's 6. I gotta have a line over there. And then all I would do is connect these, right? And just like with the left and right Riemann sums, these trapezoidal sums can be either an over approximation or an under approximation based on the way your graph curves, right? So it's not guaranteed to be an under approximation or an over. So if you want to get a sneak peek at that, that's the idea behind it. And for these trapezoidal sums, you have to use the formula for the area of a trapezoid, right? Which if you want to try to practice this yourself and you don't remember that formula, right? Let's say this is B1, B2, and this is H, right? You got 2 different bases in a trapezoid. You got this one, you got this one. The formula for the area of that thing is, what's the best way to write this? I'll write it like this: B1 plus B2 over 2 times H. So if you think about it, this is kind of like an average of the bases. Kind of takes the average base times the height. So that's the area formula, and that's how we would calculate each of these trapezoids. So trapezoidal sums take a lot more work, that's for sure. But they do tend to be a lot more accurate too, because they sort of adjust. By creating that slanted connection there, they adjust for how the curve is moving a little bit more accurately. So anyway, just another type of sum to, keep in the back of your head on the horizon, because there are some FRQs that ask about that. And so we'll get to that in class later, but I want to go ahead and just keep you all doing Riemann sums right now. Anyway, take care. Have a good weekend. Love you guys. Stay safe.